Welcome, fellow travelers, to a journey through time. We're going back billions of years to Earth's earliest chapter, the Precambrian era. Imagine a time before dinosaurs, before plants, even before oxygen. From a swirling cloud of gas and dust, our planet emerged, a hot, molten sphere bombarded by cosmic debris. This is the Hadean Eon, a time of intense heat and chaos. But from this fiery cradle, life would eventually spring. Join me as we unravel the secrets of Earth's ancient past and uncover the story of how our planet became the vibrant, life-sustaining world we know today. Our first stop is the Hadean Eon, a billion-year interval named after the Greek underworld, Hades. Temperatures were scorching, the surface a magma ocean, constantly bombarded by asteroids and comets. As Earth cooled, a crust formed, our planet's first solid ground. Water vapor condensed into clouds, leading to torrential rains that lasted millennia. Oceans began to form, setting the stage for life's grand entrance. The Archean Eon followed, marked by the emergence of the first continents. It was a world vastly different from our own, yet it was here in this alien environment that life first took hold. The origins of life are a profound mystery, a puzzle scientists are still piecing together. But we know it happened during the Precambrian, in those primordial Archean oceans. Picture a planet devoid of oxygen, where single-celled organisms, the pioneers of life, first appeared. These early life forms were simple yet remarkably resilient. They thrived in extreme environments, harnessing energy from chemicals, not sunlight. Let's venture into the depths of Earth's remarkable past. Let's journey back to 4.6 billion years ago, the very beginning of the Hadean Eon. Picture, if you will, a young Earth still forming. Our planet was a swirling mass of dust and gas, colliding particles generating intense heat. The surface was a churning ocean of magma, constantly bombarded by asteroids and comets left over from the solar system's formation. These impacts, some colossal in scale, delivered even more energy to the young Earth, keeping it in a molten state. A sky ablaze with fiery streaks as these celestial bodies crashed into the Earth, vaporizing upon impact. The energy released would have been unimaginable, making the surface uninhabitable for any life forms we know of today. Yet, amidst this chaos, the building blocks of our planet were being assembled. The Hadean Eon was a period of intense turmoil, but it was a necessary prelude to the emergence of life. As we move through the Hadean Eon, a gradual transformation takes place. Earth, no longer receiving constant energy infusions, starts to cool down. This cooling marks a pivotal moment in our planet's history, for it allows the formation of the Earth's crust. The molten rock, glowing red-hot, slowly cools and solidifies, forming a new solid surface. Like a cooling vat of molten metal, a thin, brittle crust forms atop the still liquid magma below. This nascent crust was constantly being broken and reformed by volcanic activity and the remaining asteroid impacts. With the formation of the crust, another crucial element comes into play: liquid water. Water vapor rises into the primitive atmosphere, eventually cooling and condensing to form the first clouds. Over millions of years, these rains filled the low-lying areas, forming the first oceans. As the Hadean Eon gives way to the Archean roughly 4 billion years ago, we witness the emergence of the first continents. These early landmasses were not the vast, stable continents we know today. They were smaller, fragmented, and constantly reshaped by the intense geological activity of the time. Volcanoes played a crucial role in this process. They erupted continuously, spewing molten lava onto the Earth's surface, gradually building up the landmass. These volcanic eruptions also released gases from the Earth's interior, contributing to the developing atmosphere. The atmosphere of the Archean, however, was very different from our own. It was a toxic mix of methane, ammonia, and other gases, devoid of free oxygen. The Archean Eon was a time of immense geological upheaval and chemical experimentation. The atmosphere of the early Archean Eon was a far cry from the life-sustaining blanket of air we breathe today. It was a toxic, alien atmosphere hostile to most life forms we know. Think of a sky painted in hues of orange and brown, thick with volcanic gases and devoid of the refreshing blue we associate with our sky. Volcanic eruptions, occurring with much greater frequency than today, spewed massive amounts of carbon dioxide, methane and ammonia into the atmosphere. These gases trapped heat, creating a greenhouse effect that kept the Earth much warmer than it is today, despite the sun being fainter at the time. The lack of free oxygen was perhaps the most significant difference between the Archean atmosphere and our own. While this early atmosphere may seem inhospitable to us, it was within this alien environment that life emerged and thrived. The very conditions that seem so hostile to us were essential for the first chapters in the grand story of life on Earth. In the primordial soup, the dawn of life, the question of how life arose from non-living matter is one of the most fundamental and challenging questions in science. While we don't have all the answers, we have tantalizing clues that point to a remarkable story unfolding in the Archean Eon, in the warm, chemically rich waters of our planet's youth. Imagine, if you will, these early oceans, not the vast blue expanses we know today, but shallower, warmer, and teeming with a diverse mix of dissolved minerals and gases. Scientists call this the primordial soup, a rich broth of organic molecules constantly being energized by volcanic heat, lightning strikes, and the sun's ultraviolet radiation. This wasn't just any soup, however, it was a crucible where the basic building blocks of life, amino acids, nucleotides, and lipids, were spontaneously forming and interacting. It's a story of chance and necessity, where the improbable became inevitable, paving the way for the incredible diversity of life we see today. As we delve deeper into the mystery of life's origins, one intriguing theory emerges: the RNA world hypothesis. This hypothesis proposes that RNA, not DNA, was the primary carrier of genetic information in early life forms. But why RNA? What makes this molecule so special? RNA, like DNA, can store genetic information, but unlike DNA, it's a simpler molecule capable of both storing and expressing genetic information. This dual functionality is crucial, as it suggests that early life may have relied on RNA for both inheritance and catalysis, the speeding up of chemical reactions necessary for life. In the primordial soup, RNA molecules could have been the versatile agents, storing genetic data and catalyzing the chemical reactions that gave rise to life. These RNA enzymes, or ribozymes as scientists call them, could have facilitated the replication of genetic material and the synthesis of proteins, essential functions for any living organism. The RNA world hypothesis is supported by the fact that RNA still plays vital roles in modern cells, particularly in protein synthesis. While the RNA world hypothesis is still debated, it offers a compelling explanation for how life may have bridged the gap between non-living matter and the complex DNA-based life we see today. From simple beginnings, the rise of prokaryotes. The first life forms to emerge on Earth were prokaryotes, single-celled organisms lacking a nucleus and other membrane-bound organelles. These microscopic pioneers, while simple in structure, were remarkably successful, colonizing the early Earth and forever altering its chemistry. These small cells might have been the sole inhabitants of a world where they thrived in environments that are now hostile to most life forms. Some prokaryotes, known as extremophiles, even evolved to tolerate extreme conditions, such as the scorching heat of volcanic vents or the highly acidic waters of sulfur springs. These early prokaryotes were also incredibly diverse in their metabolic capabilities. Some, like plants today, evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into energy. The rise of prokaryotes marked a pivotal moment in Earth's history. While the primordial soup hypothesis is widely accepted, another intriguing theory suggests that life may have originated in a more specific and dramatic setting: deep-sea hydrothermal vents. These vents, found along mid-ocean ridges where tectonic plates spread apart, spew forth hot, mineral-rich fluids from the Earth's interior. Let's imagine descending into the abyssal depths, where sunlight never penetrates. Here, in the crushing pressure and perpetual darkness, lie these hydrothermal vents, oases of life in an otherwise barren landscape. These vents release a cocktail of chemicals, including hydrogen sulfide, methane, and hydrogen, providing a potential energy source for early life. The steep temperature and chemical gradients found at hydrothermal vents could have created natural cells, tiny compartments where organic molecules could concentrate and interact. Some scientists believe that the first self-replicating molecules may have arisen on these mineral surfaces, taking advantage of the unique chemical environment found there. This theory highlights the potential for life to exist in even the most extreme environments, both on Earth and perhaps on other planets and moons in our solar system. In the annals of life on Earth, few events have been as transformative as the evolution of oxygenic photosynthesis. This process, pioneered by humble cyanobacteria, would forever alter the course of our planet's history, paving the way for the emergence of complex life and shaping the very air we breathe. A world bathed in the warm glow of the early sun, where life existed in a state of anaerobic contentment, utilizing chemical energy sources like sulfur and iron. Then enter the cyanobacteria, microscopic alchemists with a revolutionary capability, the ability to harness sunlight to split water molecules, releasing a byproduct previously unknown in any significant quantity: oxygen. These early cyanobacteria, also known as blue-green algae, were simple organisms, but their impact on Earth was anything but. As they diligently went about their business of photosynthesis, releasing oxygen as a waste product, they inadvertently set in motion a chain of events that would transform the planet. This gradual but relentless oxygenation of the atmosphere, known as the Great Oxidation Event, marked a turning point in Earth's history, setting the stage for the evolution of complex multicellular organisms, including ourselves. The Great Oxygenation Event, or GOE, occurred roughly 2.4 billion years ago. It marked a shift from methane and ammonia to oxygen in Earth's atmosphere. Cyanobacteria produced oxygen, changing the atmosphere's color. This transformation took millions of years. Oxygen reacted with iron in oceans, forming banded iron formations. Once iron was saturated, oxygen built up in the atmosphere. This had profound consequences for life. Anaerobic organisms found oxygen toxic. They had to adapt, retreat, or face extinction. Some evolved to utilize oxygen for respiration. This allowed for more efficient energy generation. It paved the way for complex multicellular organisms to evolve. The Great Oxygenation Event's fingerprints are etched in the rocks beneath our feet. Geologists have uncovered evidence of this ancient atmospheric revolution. Banded iron formations dating back to the GOE are key evidence. These layers tell a story of oxygen reacting with dissolved iron in the oceans. Before the GOE, iron was soluble in oxygen-poor oceans. Rising oxygen levels formed insoluble iron oxide settling on the ocean floor. This created the distinctive layers of iron oxide in banded iron formations. The scale of these formations shows the massive oxygen production by early photosynthetic organisms. They remind us of the profound transformation driven by microbial life. Other geological clues further corroborate the story of the GOE. These records provide tangible evidence of this ancient atmospheric revolution. The Great Oxygenation Event was a double-edged sword for life on Earth. It led to ecological diversification and the evolution of oxygen-breathing organisms, but it also caused a mass extinction of anaerobic life forms. Oxygen allowed for more efficient energy generation and complex life. However, it was toxic to many ancient organisms. Survivors adapted to oxygen-deprived niches, showcasing life's resilience. Our journey through the Precambrian takes us now to a grand, slow-motion ballet, the dance of the continents. We're used to thinking of the continents as fixed, but over billions of years they drift across the globe, colliding and splitting apart in a process called plate tectonics. This dance has shaped Earth's history, influencing everything from climate to the evolution of life. The Precambrian era saw the formation and breakup of several supercontinents, vast land masses that assembled like giant jigsaw puzzles. These supercontinents, with their imposing sizes, influenced ocean currents, atmospheric circulation, and the distribution of life on a global scale. Before the familiar Pangaea, which formed much later in Earth's history, there were earlier supercontinents, each with its own unique story to tell. One of the earliest and most well-known of these Precambrian titans was Rodinia, a name derived from the Russian word for homeland. Rodinia's assembly and breakup, spanning hundreds of millions of years, had profound consequences for Earth's climate, the evolution of early life, and the distribution of mineral resources we rely on today. Let's take a closer look at the story of this ancient supercontinent. Around 1.1 billion years ago, Earth's tectonic forces assembled the supercontinent Rodinia, a colossal landmass surrounded by a vast ocean. Rodinia's formation altered ocean currents and weather patterns, possibly triggering the snowball Earth events. Life thrived in Rodinia's shallow seas, setting the stage for future diversification. No supercontinent lasts forever. Rodinia's breakup began around 750 million years ago. New ocean basins opened, altering currents and climate. Volcanic activity released greenhouse gases, warming the planet. The breakup created nutrient-rich coastlines, fostering life. Rodinia's legacy is seen in today's geological formations, a powerful reminder of Earth's dynamic nature and its incredible capacity for transformation. The Precambrian oceans were vastly different from their modern counterparts. Picture a world where the seas were not blue, but a murky green tinged with iron and other minerals. These early oceans were a dynamic chemical cocktail, constantly evolving as life emerged. One of the most significant differences was the oxygen content. For much of the Precambrian, the oceans were largely anoxic, lacking significant oxygen. This limited life to anaerobic organisms. Photosynthetic cyanobacteria released oxygen, transforming the oceans. This transition had profound implications for marine life. In the sunlit waters of the Precambrian seas, stromatolites flourished. These rock-like structures, built by microorganisms, are some of the earliest evidence of life on Earth. Picture yourself wading into a sea, the bottom covered in rocky mounds. These are stromatolites, intricate ecosystems built by microscopic life. Cyanobacteria, photosynthetic pioneers, are the key architects. They form mats that trap sediments, building layers of rock. As the mat grows, it creates the layered structure of a stromatolite. Stromatolites thrived in the Precambrian, where few life forms could exist. Their photosynthesis oxygenated the atmosphere, paving the way for complex life. Today, stromatolites are rare, found in isolated locations mimicking ancient Earth. These living fossils remind us of life's tenacity in its earliest forms. As the Precambrian era ended, the Ediacaran fauna emerged, marking the first widespread appearance of macroscopic multicellular life. These soft-bodied organisms discovered in Australia were diverse, with various body plans and ecological strategies. Despite lacking hard parts, they represent a turning point in life's history, a prelude to the Cambrian explosion. The Precambrian, once considered barren, holds whispers of ancient life preserved in stone. Visualize yourself as a geological detective, chipping away at rock layers, uncovering Earth's history. These fossils reveal a vibrant Precambrian biosphere, challenging our assumptions about early life. Among the most striking legacies of the Precambrian are stromatolites, built by cyanobacteria. These ancient reefs, over 3.5 billion years old, showcase microbial power. Imagine venturing into a lagoon surrounded by rocky domes. These are stromatolites, resembling petrified cauliflowers. Unlike coral reefs, stromatolites are built by microbes. Cyanobacteria form mats that trap sediments. Over time, layers accumulate, creating stromatolites. They grow upward, leaving a growth record like tree rings. Stromatolites thrived in harsh Precambrian environments. Their photosynthesis oxygenated the atmosphere. These ancient structures are rare in modern times, mostly confined to specific habitats. These living fossils remind us of the impact of small organisms. While stromatolites provide a macroscopic window into the Precambrian world, the true diversity of early life is revealed in the microscopic realm of microfossils. These tiny remnants of ancient cells, often no larger than a grain of sand, preserve exquisite details of cell walls, filaments, and even internal structures, offering a glimpse into the cellular machinery of life's earliest chapters. Peering through a powerful microscope, transported back billions of years to a time when the oceans teemed with a bewildering array of single-celled organisms. Their delicate forms preserved in chert, a fine-grained, silica-rich rock that faithfully replicates even the finest details. These microfossils represent a diverse range of early life forms, including bacteria, archaea, and early eukaryotes, the lineage that eventually gave rise to plants, animals, and fungi. By studying their morphology, chemical composition, and isotopic signatures, scientists can reconstruct their metabolic pathways, ecological roles, and evolutionary relationships. One of the most exciting discoveries in recent decades has been the identification of fossilized lipids or fats preserved in Precambrian rocks. These biomolecules, more resistant to degradation than DNA or proteins, provide further evidence for the antiquity of certain groups of organisms and offer clues about their metabolic capabilities. The study of microfossils is a meticulous and challenging endeavor, requiring specialized techniques and a keen eye for detail. Yet the rewards are immeasurable, for these tiny fossils hold the key to understanding the origins of life itself and the extraordinary journey that led from single-celled ancestors to the complex tapestry of life we see today. Our planet has undergone dramatic transformations, continents colliding, oceans changing color, and life emerging against all odds. The Precambrian climate swung between extremes from intense heat to global glaciation. Volcanic activity and atmospheric changes played key roles. Early Earth was much hotter due to volcanic greenhouse gases, creating an inhospitable climate. Photosynthetic organisms like cyanobacteria helped cool the Earth by absorbing carbon dioxide, leading to a more temperate climate. The Precambrian climate continued to fluctuate, with episodes like the Snowball Earth events encasing the planet in ice, a frozen embrace. A world where ice dominates the landscape, where glaciers stretch from pole to pole and the average global temperature plummets to -50 degrees Celsius. Geologists have uncovered evidence for snowball Earth events around 2.4 billion and 700 million years ago. These events were marked by runaway ice albedo feedback loops. As ice sheets expanded, they reflected more solar radiation, further cooling the planet and accelerating ice growth, encasing the oceans in ice kilometers thick and pushing life to the brink. But life found a way to endure in isolated pockets of liquid water, such as near hydrothermal vents or in areas where volcanic activity melted the ice. These refuges may have served as cradles of evolution. The snowball Earth events likely spurred evolutionary innovations. Our journey through the Precambrian has taken us from the fiery birth of our planet to the emergence of the first single-celled organisms. The elements that make up our bodies, the carbon, hydrogen, oxygen, and nitrogen, were forged in the hearts of stars. These elements coalesced into new solar systems, including our own. So, in a very real sense, we are all stardust. The building blocks of life were present in the gas and dust that formed our solar system. Energized by volcanic heat, lightning, and the sun's radiation, these ingredients self-assembled into complex molecules. The exact details remain a mystery, but it likely happened in the warm, chemically rich waters of early Earth. The Precambrian era witnessed the transformation of our planet from a lifeless rock to a cradle for life. As we look back across billions of years, the Precambrian reminds us how every moment in Earth's history echoes through deep time. The planet's earliest chapters, though shrouded in mystery, set the stage for everything that would follow, from the first stirrings of life to the dazzling diversity we see today. Each rock, each fossil, is a silent witness to the struggles and triumphs of life's earliest pioneers. Our own existence is intertwined with this ancient legacy, a testament to resilience, adaptation, and the relentless march of evolution. The story of the Precambrian is not just Earth's story, it's ours as well, written in the very atoms that make us who we are. Thanks for watching. Like, share, and subscribe for more.